Okay, this video is on areas of regular polygons and composite figures. And first we need to define a few terms in a regular polygon. So the center of a regular polygon. Notice how I have a regular polygon here with a circle circumscribed around it. So our polygon is inscribed in a circle. The center of that circle is also the center of our polygon, which is O. The radius is the radius of the circle. So from the center of our polygon out to one of the vertices of our polygon. So that would be an example of OF. OE would be another example. OD would be another example. And your central angle. Your central angle then is the angle where you're going from one vertice to the center to another exact adjacent vertice. So in this example, it would be angle FOE. And make sure you put a little angle symbol in front of it. Now the apothem is a new term for you. The apothem is from the center perpendicular to a side of our polygon. So in this example, our apothem is segment OX. Okay, example 1 is very similar to what we just did. So in this figure we have a pentagon that is inscribed. Okay, so our pentagon is inscribed inside a circle X. Identify the center, radius, and apothem, central angle, and find the measure of our central angle. So our center, it's the center of our circle, like I just had, X. The radius is from the center to one of the vertices. So we have XQ drawn in and we have XR drawn in. So either one of those would work. Yeah, technically XP, XT, XS, I would technically accept those too. Remember, your apothem is from the center perpendicular to a side of our polygon. So in this case, that's segment XN. The central angle symbol in front is from a vertice to the center to another adjacent vertice. So angle RXQ. RXQ. Now the measure of the central angle. To figure that out, take 360 and all of these central angles. So that angle, this angle, this angle, that angle, and this angle are all congruent. So we take 360 and we divide by the number of sides that we have, because that's how many central angles we have. So in this case, it's 360 divided by 5, and we get 72 degrees. Okay, one of our main goals in this section is to find the area of these regular polygons. So the tabletop is shown of a regular hexagon with a side length of 3. So it's a regular polygon, so each one of these side lengths is 3. And our apothem is 1.7 feet. What is the area of the tabletop to the nearest tenth? So each one of these is a triangle. Triangle, 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 triangle. All of those are all congruent. So I have 6 triangles times by the area of a triangle, which is 1/2, base, which is 3, times by the height. The height is this apothem length, so that is 1.7, and we get 15.3 square feet. Now notice what we had here. 1/2 number of sides times the side length. That's the perimeter of our polygon times by the apothem. So now let's talk about this in a general case. Area of a regular polygon. Okay, you have 1/2. Let's look at what we just did. Our side length. because that was the base of each one of these triangles that we would see in here. Let me draw in the radii so that you can see we have this many triangles times by the number of triangles that we have. So 1/2 base times the number of triangles times by the apothem, which is the height of that triangle. So let's look at what that really is. The number of sides times our base. Let's name that side length. Let's make that a little bit clearer. Our side length times the number of sides, that's the same thing as perimeter. And then the apothem is that perpendicular. So 1/2 perimeter times the apothem. The shorthand for that is 1/2 apothem times perimeter. I don't know why I always put apothem first. Okay, so this is the general formula we're always going to use for areas of regular polygons. Okay, this example. Find the area of this regular hexagon. A hexagon has 6 sides. So that means that each one of these angles is 60 degrees. That makes this smaller triangle a 30, 60, 90 triangle, where this is 30, this is 60, and that's our right angle. So 30, 60, 90 triangle. The side opposite the 30-degree side is the smallest side. This side length is 5. When we have a hexagon, each one of these triangles that we drawn in there is an equilateral triangle. So that means my hypotenuse is 5. The shorter leg is half of that, so 2.5. The side opposite the 60-degree side is 2.5 root 3. So what we have going on here, okay, is a 30, 60, 90 triangle. When it's a hexagon, I want you to give this to me in simplest radical form. So keep that in mind, simplest radical form. That's why I found this in terms of radicals. So 1/2. The length of the apothem, which is 2.5 root 3 times by the perimeter. Well, the perimeter, we have 5 for each side length times the number of sides, which is 6. So this simplifies all to 37.5 root 3 square meters. Now finding the area of this regular pentagon. This is a little bit more complicated because in this case we have to use trigonometry. This whole big central angle is equal to 360 divided by 5 because that's my number of sides. And we did that in an earlier problem. I don't know why I'm typing it in my calculator. That's 72. But this apothem, since these sides are equal, the radii are all equal, this apothem cuts our isosceles triangle basically into 2 congruent triangles. So this angle right here and that angle right there are each equal to 36. I need to use trigonometry to find dB, which I'm then going to multiply by 2 to get AB. So let's look at that. dB is the opposite side. For opposite, we use sine of 36 is equal to opposite dB over the hypotenuse, which is 9. So 9 times the sine of 36. 9 times the sine of 36. That's equal to 5.3. So this is 5.3. The whole segment then, AB, this is 5.3, is twice that, which is 10.6. So that's my side length. Remember, we're going to fill in 1/2 the apothem times by the perimeter. I have 5 sides times by 10.6. Now my apothem length. This length here is the adjacent side to that 36. So for adjacent, we use cosine of 36 is equal to CD over the hypotenuse, which is 9. So 9 cosine 36 is equal to CD. And we get 7.3. That's our apothem length. So now it's just a matter of plugging in to our calculator 0.5 times 7.3 times 5 times 10.6, which I get 193.45. And I was thinking about something, that's why I wrote a C there, and you guys who were in class the other day will realize that my original calculator guy, make sure you have a calculator that has sine, cosine, and tangent on it for the test. And OC, you know who you are. Okay, composite functions. What composite functions are a bunch of or composite areas, I should say, are where you have an irregular figure. This isn't a figure that we can easily find the area of. But what we can do is we can break this up into areas that we know. This right here is a rectangle. So I have 32 times 16. So the area of this is 512. The area of this triangle, 1/2 base times height. So 1/2 my base, which is 32, times my height, which is 15. This is 240. Now this area and this area make a circle. Pi r squared. So pi, my radius is 8 squared, half the diameter. For that, I get 64 pi. So adding my area together, 752 plus 64 pi square feet. Now what is that? I got to grab my calculator. 752 plus 64 pi. We get 953.1 square feet. Sometimes your composite areas have a hole in the middle. So find the area of the big rectangle. Okay, my big rectangle. This is 100 feet. I add to it 25 and 25. So this whole width here is 150. My height, this is 20. I add 25 and 25, so that's 50. So 20, that would be 70. So find the area of 150 times 70. And that is 10500. Subtract from it the white area. So subtract from this the area of this rectangle, which is 100 times 20, which is 2,000. And we get our total area of 8,500 square feet. Okay, the last one is you have kind of an irregular figure in the plane. Again, try and break this up into areas that you can recognize. Hopefully you see right away, if you draw along the x-axis here, you have a triangle up here and a triangle down there. I'm going to call them x and y. So the area of triangle x, 1/2, my base length, which is 4, 5, 6, times by the height from one vertex perpendicular to that base that we just found, which is 2. So that area is equal to 6. We're going to add to it the area of this other triangle, triangle y. 1/2 base times my height, which is also 2. Oh, look, 6. Add those two areas together, and we get 12. Okay, so that is your areas of regular figures and composite functions. Please now work on the homework for me.